full screen. And very briefly, I was just saying how I'll talk about topological phonons, but to start with something that may be more familiar to most people, I'll start with topological electrons and then try to motivate topological phonons. And to understand topological electrons, perhaps the simplest system we can think of is what's called a topological insulator. And to understand how that comes about, I can take the example of what we now call a normal insulator, like diamond, shown here on the left. And diamond is a semiconductor or an insulator. It means it has a band gap. So the valence band in blue is separated by energy gap from the conduction band in red. And I know diamond is indirect, but for the purposes of this depiction, I just plot it as a direct band gap semiconductor. It doesn't really matter. And then what we can do in diamond, you can imagine that you pick the carbon atoms that make up diamond and you pull them apart, as shown on the right of the diagram, all the way to the edges of the universe. So every carbon atom at one edge of the universe. And this is what we call the atomic limit. And in the atomic limit, the system is also insulating. The electrons cannot travel through different carbon atoms. And in a system like diamond, you can go from the crystal limit to the atomic limit. And throughout this process, you can maintain a band gap in the system all along, as shown by the diagrams at the bottom. Now, if we compare this to a different semiconductor, in this case, bismuth selenide, then on the crystalline side on the left, we also have a band gap. And if we pull the crystal apart on the right-hand side in the atomic limit, we also have a band gap. So the starting and end points look the same. Both are also insulating. But in the case of bismuth selenide, it's actually impossible to go from one side to the other without somewhere in the middle closing the band gap. And that's shown by the bottom diagram in the middle. Now, this is a fundamental difference between diamond and bismuth selenide, which allows us to tell apart what we now call a normal insulator like diamond and a topological insulator like bismuth selenide. The key difference between the two is that the crystalline parts, which look the same naively in the sense that they both have a band gap, fundamentally are different. And the reason for that is because in bismuth selenide, as you cross the Brillouin zone, the electron wave function acquires a twist. And that twist that the electron wave function has in the crystalline side is not there in the atomic limit on the right. So to go from the crystal to the atomic limit, you must undo this twist to the wave function. And the only way in which this twist can be undone is by going through this intermediate metallic state. So these wave function twists, we can characterize them with topological invariance. I represent them here with where I've mixed the coloring of the bands. Sometimes it's called the band inversion. And this places a fundamental difference between bismuth selenide, which we call a topological insulator, and diamond, which we don't. So in bismuth selenide, the wave function has an extra twist compared to diamond. Now, this is a very broad and naive description of what topological insulators are, but one very important aspect of topological insulators and topological materials in general is what happens here in the middle, where the system goes from having a twist in the wave function to not having that twist in the wave function. Because something dramatic must happen at that point, and what typically happens is that you have this metallic state. And this leads to a very important concept, which is called the bulk boundary correspondence. So if you think about a lump of bismuth selenide in the lab, then the surface of that material is really a boundary between the bulk of the material and the outside, which is typically air or vacuum. And air or vacuum are topologically trivial, whereas the inside, in this case, is topologically non-trivial. So the surface of the material must be the point shown here in the middle of the diagram where the wave function twist becomes undone. So that means that the surfaces of topological materials will have some sort of interesting metallic state associated with them. And that state has some interesting features because it's determined to be there by the underlying topology of the system. This general relationship between a bulk topology and the surface state or boundary state is called the bulk boundary correspondence. And these surface states are what really make topological materials interesting. So just to give you a few examples, so I've been discussing topological insulators like bismuth selenide as a simple example. And in this particular case, these surface states are spin currents. So electrons of opposite spin travel in opposite directions, and they are robust. That means they're forced to be there by the underlying topology, and there is some protection to scattering. But the family of topological electronic materials is much, much wider than topological insulators. And here at the bottom, I have another example of a type of topological insulator, in this case called a Chern insulator, which is essentially a combination of topological insulator with some sort of magnetic order. And in this case, we also have the same ideas, but their specific form is a bit different. So in this case, the bulk topology is described by a different topological invariant, happens to be the Chern number. And the surface states, rather than being spin currents, now become charge currents. And you could go on. So there are many other types of topological order. There's topological superconductors and semimetals, and they also have their own bulk boundary correspondences. So the specific type of topology I'll be most interested in today, because that's the most pervasive one in phonons, is what we call topological semimetals. So here I'm still talking about electrons, but we'll get to phonons in a moment. And topological semimetals, in this case, Weil semimetals, are materials where you have band crossings, which are in the bulk, which are protected by topology. And this is an example of one of the first experimental discoveries of a topological semimetal, tantalum arsenide. The second diagram shows the bulk topology. In a sense, you have these crossing points, which are nodes in reciprocal space that carry this topological charge, which again you can characterize with a Chern number. And in this particular case, the surface states are what we call Fermi arcs. So you project the bulk topology to the surface, and then this green curve uniting the blue and red projections is what we call a Fermi arc, which again is some sort of localized surface states connecting the projections of the bulk crossing points. And on the right, I'm just showing the experimental the discovery of these in tantalum arsenide, where you're comparing the theoretically calculated surface states with the experimentally resolved surface states using RPES. So if we take a step back, and as I said, today we'll mostly discuss topological crossing points, because those are the important ones for phonons, then it's actually very easy to understand why these crossing points between two bands are very robust in 3 dimensions. So at the top, I have a very simple Hamiltonian for a two-band model. So H is my Hamiltonian, and then Q is my wave vector in reciprocal space from some reference point, which is the crossing point. And then the sigma are the Pauli matrices. So this is the usual two-band model written in the Pauli matrix spaces. And such a Hamiltonian has the electron dispersion shown at the bottom, and that's essentially two bands crossing like this, as shown in the diagram. Such crossings in 3 dimensions are extremely robust. And the reason for that is because if you imagine adding a perturbation to your Hamiltonian, like I'm doing at the bottom, so this V is a general perturbation potential, then the most general form in which I can write this potential is again something depending on the 3 Pauli matrices, M1, sigma 1, and so on. And then if I add that potential as a perturbation to my original Hamiltonian, then I can see that all that happens is that my crossing point becomes offset. So rather than being at 0, 0, 0, it's now at minus M1, minus M2, minus M3. So adding a perturbation to the system does not remove the degeneracy of the two bands. All it does is it displaces the crossing point somewhere else in the Brillouin zone. But otherwise, it's extremely robust. And this is just a very simple argument using a two-band model, but you can actually characterize this topologically. And what you can do to understand the topological protection of this is you can build a surface around the crossing point, and then on that surface, you can calculate what's called the Chern number. And the Chern number happens to be +1 or -1, and that reflects that there is a topological obstruction to removing this crossing point. So these are in the electronic context, these are called Weil points. As I showed in the previous slide, they have already been observed in a range of electronic systems. So why phonons? So what I want to do now is I want to describe how all of these ideas also occur in phonon systems, and how studying them in phonon systems may actually be will provide different angles to what we have when we study them in electronic systems. So in order to understand why phonons could be useful, we can try to understand why, what do we need to have topological order in electronic systems. And this is true for either a topological semi-metal or topological insulator. So on the left, I'm showing a topological semi-metal, where I have this crossing point, which is protected by some topological invariant. And on the right, I have a topological insulator, which again is described by some topological invariant. And electronic systems are very interesting because, for example, electrons are charged. So that means that we can manipulate electrons using things like electric fields, which is very convenient. However, electrons have a particular limitation, which is the fact that they are fermions. And as fermions, they're described by Fermi-Dirac statistics, which means that of all the electrons that you have in a crystal, you can really only access those electrons very near the Fermi level. So if the Fermi level happens to be right at the topological crossing point, like in the left diagram, or in the middle of the band gap, like in the right diagram, then that's great, because that means that the electrons that you can access are those very close to this topological feature, and therefore you can explore the topology associated with those electrons. The problem is that you may have these interesting band structures in other places of the energy spectrum, which are either very far below the Fermi level or very far above the Fermi level. And those in general will not be accessible to your system. So that means that although, in fact, as I've discussed just a moment ago, this 3D crossing point should be very robust in electronic systems, we don't have that many examples. And the reason for that is because they often happen very deep in the valence bands or very high in the conduction bands, and therefore we cannot access them. It's only when they happen at the Fermi level that we can really access them in electronic systems. So in a sense, this is a limitation of electronic systems, that we need to be lucky and have the Fermi level where the interesting topology happens. Now, what about phonons? And now you can see where I'm going, probably. So phonons are not charged, so that's a disadvantage if you want. So it may not be as easy to play around with phonons and so on, and that's probably why they have received so much attention. But on the other hand, phonons are bosons, and that means that they're described by Bose-Einstein statistics. So that means that we can actually access the entire phonon spectrum, and wherever the topological bands occur, we can access them in principle. So that's very different from electrons. And that means that actually topological phonons may be found in pretty much all materials, because we can access the entire spectrum of the entire spectrum. So this is essentially the point I want to make in the first half of the presentation, and to give you some examples of how this comes about. And then in the second part of the presentation, I'll talk about some very recent developments in the area of topology, what's called multi-gap topology. And there we'll argue that phonons are not only advantageous in some respects compared to electrons, but actually phonons may be the only way to actually study this multi-gap topology I'll describe at the end properly. So that's the key. The full phonon dispersion can be probed for topological phonons, as opposed to the limitations to the Fermi level for topological electrons. Okay, so here I have an example of a material that we found exhibits a range of topological phonons. So this is a very well-known perovskite oxide, barium titanate. And what I'm showing on the left is some of its structure. So at high temperature, this material has a cubic structure. And then as you lower temperature, it undergoes a number of structural phase transitions, the first one of which is to a tetragonal structure, shown by the second crystal, where there is an off-centering of the titanium atom in the center. So if we want to describe this type of material using, if we want to study the phonons of this type of material, the phonons typically at the harmonic level will have imaginary phonons, because they indicate that you have distortions in the system. You have directions in which the energy becomes lower, and that's what I'm showing on the right diagram. So the dashed line is the harmonic calculation of the tetragonal phase of the system, and you can see that around gamma and X and gamma and Z there is an imaginary branch, and that indicates that if you distort the system along that branch, you'll get to a low energy structure that is actually present at lower temperatures. But this tetragonal structure does exist in the temperature range around room temperature. And the reason for that is because of anharmonic vibrations in the system. So if you repeat the phonon calculation at 300 Kelvin, including anharmonic vibrations, then you get the green curve, which are indeed stabilized. What we did instead of studying the system as a function of temperature is actually study it as a function of photoexcitation. And that's a rather new direction of studying these materials. And the reason for that is because we think light provides a more versatile means of controlling these materials that we'll see in a moment. We'd like to control the topology of these materials. So light is a good means to do so. So it turns out that just like you can stabilize this material with anharmonic lattice dynamics driven by thermal motion, you can also stabilize these phases by shining a laser at them, so creating a photoexcitation in the system. So in the ground state, you have this typical double well potential where the system wants to go to one of the two sides of the double well, and when you create a photoexcitation, the potential energy landscape becomes a proper minimum, so the system stays put in that structure. And what I'm showing here now is the phonon dispersion under some amount of photoexcitation. And what we have here is an example of a wide number of topological features in a phonon dispersion. So I'm showing it in various ways. So in the middle diagram, I'm showing the phonon dispersion along a particular high symmetry line. And I'm indicating some of the key points, which I'll discuss a bit more detail in a moment. So a novel ring, triple Weyl point, and so on. And then on the right-hand side, I'm showing the Brillouin zone of the material. And again, in that Brillouin zone, plotting the various topological features that we have in the system. So as I said, crossing points in 3D are rather robust, and that's what we have here. So for example, at the very top of the Brillouin zone, we have these cones, which are yellow and sort of brownish. And each of those cones corresponds to a Weyl point, so a topologically protected crossing point in the phonon dispersion. And you can see that we have 8 of them. So the reason why we have 8 of them is because in reality we have a pair of them, one with a positive Chern number or chirality and the other one with a negative one. And then because of the crystal symmetry of the system, then they just get repeated, and you have 8 of them. But then the other interesting thing is that we don't only get individual crossing points, but we actually get lines over which we also have degeneracies in the phonon dispersion. And this is just a simple extension, if you want, of the idea I described at the beginning about the robustness of crossing points when you add crystal symmetries. So crossing points, as we saw, are generic. They don't need the crystal symmetry in 3D to protect them. But if you add crystal symmetries on top, then that means that you can go from a point to a whole line that's protected by that particular symmetry. So in this particular system, you have 2 mirror planes, MX and MY mirror planes. And on those 2 mirror planes, you have these whole nodal loops or nodal rings in red that are whole, essentially loops that are degenerate. 2 bands are degenerate along those entire loops. And that's yet another type of topological degeneracy that you have in these systems. And actually we have these red ones, one on the MX and one on the MY plane. And then in the Z to gamma direction, we have a nodal line, which is this brown thing going up. And if you see these purple cones, then there the 2 red nodal lines and the brown nodal loop, all 3 cross at those purple points. So there we have what we call triple Weyl points. So as you can see, you can start playing around with this starting sort of building blocks, which are the band degeneracies, and then adding symmetry on top, you can find this zoo of topological features in the band structures. And here I should say that this is only looking at a specific few bands in the region of 8 to 12 terahertz in the phonon dispersion. You can do the same in the rest of the spectrum, and you find similarly interesting topological features. And as I said, the advantage that we have with phonons is that it doesn't matter where these crossing points happen in the energy spectrum. We can in principle access them because phonons are bosons, they don't have a Fermi level. So what's also interesting about these materials and what we ultimately want to do with topological matter is we want to be able to control those topological states. And this is exactly what we're doing here. And that's why we used light to, photoexcitation is used by light to manipulate that. So essentially when you create photoexcitation, depending on the amount of photoexcited carriers, then the bonding of the system changes, and therefore the phonons change. And if we study how the phonons change as a function of this photoexcited carrier density, then we can see how the topology in fact changes. So what I'm showing here on the right diagram is an example of how that comes about. So let me walk you through that. So what we have, we start with the diagonal, the two diagonals in the system, which say creation, and at the photoexcitation density below 0.05 electrons per formula unit, there is nothing, that there are no Weyl points or anything like that in this material. But then as you increase the photoexcited carrier density at about 0.05 electrons per formula unit, you have at particular points the creation of pairs of Weyl points, and this happens along these diagonals. Then as you continue increasing the photoexcited carrier density, then these pairs of Weyl points were created on these diagonal lines, start moving away from each other across the Brillouin zone, and then eventually they meet on the vertical and horizontal lines with another Weyl node created on the other side. So they travel together, they meet, and then when they meet, they annihilate. And that's the only way in which one can remove these topological features, by annihilating them together. What I show on the left, which is the diagram I had earlier, is somewhere in the middle of this process. I think it was about 0.07 electrons per formula unit. So that's when these Weyl nodes are all there and traveling from being created to being annihilated from each other. But this shows how we can use light to essentially control where these are. And actually it turns out that in this system, in the photoexcited range from 0.07 to 0.08, we have another set of 8 Weyl points that are created and annihilated, and these are the blue and green Weyl points, also shown in the diagram here. So again, this is meant to show the richness of topological phases that one can have and manipulate in phonon dispersions. Oops. Okay, so this is up to now all I've talked about is what happens in the bulk of the system, and topology is a pure bulk property of material. So you can fully characterize the topology of a material by studying its bulk properties. But as I said at the very beginning, what makes topological materials perhaps most interesting is that this bulk topology then has some implications for what happens at the surface of the material. And this is what I'm showing now here. So the diagram on the left is showing the surface of the material, the QX, QY surface. And what I'm showing is the surface states. So as I said at the beginning, these Weyl semi-metals or Weyl crossing points have what are called Fermi arcs. In the case of electrons, here we just call them surface arcs because, of course, phonons are not fermions, but the idea is the same. So in this particular case, if you look at the top, we have these -1 + 1s are the projections of the bulk crossing points. And then we can see these lines connecting them labeled surface arcs. And these are these surface states that are associated with the bulk topology. And these states are essentially phonon states that are localized on the surface and again determined by the fact that you have bulk topology. And we have plenty of other surface features associated with, for example, these novel rings and so on. And this diagram is trying to show how some of them come about. But the key idea is that whenever we have this bulk topology, then at those frequencies on the surface, we'll have localized phonon states which have some sort of protection due to the bulk topology of the system. And this is an example of how this comes about in barium titanate. Okay, so as I said, because these crossing points, for example, are rather generic, then we think that topological phonons should be rather generic. And what we're finding is that that is indeed the case. So up to this point, I've been discussing barium titanate, but we actually have studied now a range of other materials, and pretty much in all of them, we've been encountering interesting phonon features, phonon topological features. And here I just have a survey of a few examples of that. So here I have lead titanate, another well-known perovskite oxide, which again exhibits a range of Weyl points, nodal lines, and nodal rings. But if you look at, for example, the Brillouin zone on the right, you can see that the features are rather different from those that we had in barium titanate. And we've done the same with strontium titanate, where again we have somewhat different features to those of barium titanated lead titanate. So this is just to show that we think that topological phonons are probably ubiquitous in most materials, and not only that, but you can access them because of the bosonic nature of phonon excitations. So this was a piece of work that we did in the context of oxide perovskites, and we found that most of them do have these topological phonons, and we think that's interesting because oxide perovskites are used for a wide range of things. And here I have a diagram taken from MRS Communications where they argue how you have all these interesting multiferroic type features in these compounds. And essentially what we're arguing is that we're adding an extra ingredient to this family of materials, which is topology. And perovskite oxides tend to have very large band gaps, which for reasons I won't get into mean that they will not exhibit electronic topology. But as we've seen, we can still have topological order in these compounds if rather than looking at the electron bands, we look at the phonon bands. So we think there's plenty of scope to explore interesting topological phenomena by themselves and also their interplay with all these other interesting properties of oxide perovskites. And just to convince you a bit more that we think topological phonons are everywhere, this is not just perovskite oxides, but in very many different materials we've been finding them. So this is another example which we think is quite neat, which is from a compound that was synthesized only a few years ago, which is a double helix SNIP. And this compound is a sort of quasi one-dimensional material where you have this chain stacked together in the system. And as such, it has some very interesting thermal conductivity properties, which are very unidirectional. And again, this material has some interesting topological features, in this case, nodal rings that are present both in the bulk, as shown by the middle diagram, and then the surface. This is actually the first example of the surface also having nodal rings. So the way in which the symmetry plays with the topology in this material leads to that interesting outcome also in the surface states. And here I have the actual surface states of this compound shown here, which again, there are a variety of them. You can access them at all different frequency ranges in the system, and essentially amount to localized phonon states which are protected on the surface of the material. So where are we at now in studying these topological phonons? And I would say that the main open questions, which is perhaps what's most interesting for today's audience and the topic of this workshop, is the surface states. So these surface states are really what could make these topological phonons practically useful, for example, because we have this localized phonon state on the surface, which have some amount of protection due to the bulk topology. And the plot I've been showing about surface states are actually calculated in a very simple fashion. So we've just taken the bulk topology, then created a surface brute force and generated those surface states using Green's functions methods. But we haven't actually looked at them directly or properly, and that's really one of the open questions that one should look at. So open questions are: what are the precise properties of these surface states? So how localized are they really to the surface, or how much they penetrate into the bulk? How does that depend, for example, on the thickness of the material? In iconic systems, it is known that the two surfaces of the material can interact with each other and then destroy the surface states. How can we experimentally probe them to robustly check all of these predictions? And also, what could be the technological applications that we could have arising from this surface topological phonon states? And then the reason why these are all open questions, I think, is because at least from a computational point of view, it's actually rather difficult to study these properties. And the reason for that is because simulating, what we do is we do all these studies using density functional theory and essentially solving the equations of quantum mechanics for specific materials. And the approach we use is to use periodic boundary conditions. Now, when you create a surface, you of course don't have periodicity in the direction perpendicular to the surface, and that means that the calculations become incredibly more computationally expensive. So things that we haven't looked at all but could play a role is what happens when you create a surface and then allow the surface atoms to relax, which is something that of course will happen in all materials. Now, in principle, what should happen, for example, is that if the bulk topology is protected by some symmetry in the system, then if the surface relaxation maintains that symmetry, then in principle that should not affect the topological surface states. But if that surface relaxation does break the symmetry, then that could affect the topological surface states. So these are just examples of open questions that we haven't yet looked at, but would definitely be very interesting for really exploring what the possibilities are for these topological surface phonon states and how we can use them in say, practical technologies. So that's sort of the open question. Can we perform direct calculations of topological phonon surface states? Ideally at the DFT level, perhaps some simple time-binding models may suffice. Okay, so this is all I wanted to say about standard topological phonons. And by standard topology, what I mean is what I've been looking from the very beginning, where we essentially have two bands, and either these two bands have a band gap and they have some sort of topological order with them, or these two bands cross at a single point, and that also has some sort of topological order in there. And in this context, I'm now going to call this stuff I've been talking about single gap topology. So single gap by the fact that you have two bands and something in the middle, or two bands that touch just at a single point in the middle. And for that reason, I call it single gap. What I want to look at now is something that has only very recently become a topic of research in the area of topology, only in the past 1 or 2 years. And that's what I will now call multi-gap topology. And I'll explain in a moment what I mean by multi-gap topology. But this is a new concept that again has originally been explored in the context of topological electrons. For the same reasons I described earlier, electrons are charged, therefore perhaps more interesting. But what I want to argue is that while in single gap topology, electrons, you can study electrons because in many materials you do still have the Fermi level where you need it to be to study their topology. And phonons provide sort of an add-on where you have perhaps interesting features because you can access the full band structure, but there's nothing fundamentally different. In the case of multi-gap topology, I want to argue that actually phonons may be the only way forward to study the exotic physics that I'll describe in a moment associated with this type of topology. So that should be exciting for all of us working on phonons. So what is multi-gap topology? So as you can probably imagine by the name, so multi-gap topology is what happens when we have more than two bands. So when we have, and the simplest case is when we have three bands. So that's shown here in the diagram on the left. And I have the bottom, the middle, and the top band. What we now have is we have a gap between the bottom and the top band where the gap may close at specific points. And then we have another gap between the middle and the top band. And that's why we call this multi-gap topology. And the simplest such case is a three-band model like this one. Why would we care about this, you may say? So the reason why this is interesting is because in a wide class of materials, and what I mean by that is materials that either have C2T symmetry, so C2 means pi rotation and T means time reversal symmetry, or PT symmetry, then you can actually show that on the C2T invariant planes and PT invariant planes, the Hamiltonian can be made purely real. And when that happens, you can characterize the nodes between these various gaps using quaternion algebra. Okay, so as a reminder, quaternion algebra, you have the 1 minus 1, and then I minus I, j minus j, k minus k. So it's an extension of complex algebra. And the key point about quaternion algebra is that it's non-abelian. So ij is equal to minus ji, and so on. So I know I've glossed over this very quickly, but one can show from this condition that I described that you can actually associate these quaternion topological charges with these points. So if we take a step back, how does that compare to what we've been discussing earlier? So what we had earlier in single gap topology is we have, in general, complex Hamiltonians, and they are characterized by things like Chern numbers and so on. Here we have multi-gap topologies in real Hamiltonians, and they're characterized by this quaternion algebra. And what makes this really interesting, of course, is the non-abelian part of the quaternion algebra. Because as we all know, if we can braid non-abelian quasi-particles, then that is one of the strategies used to encode quantum information. So as you may know, perhaps the biggest leader in the field in this area is Microsoft. They're trying to pursue topological quantum computers by trying to build non-abelian charges in real space through Majorana fermions, for example, and the idea is then to braid them to encode quantum information. Here what we have is a very similar concept, but now the non-abelian charges are a crossing point in reciprocal space. So if you want, this is the reciprocal space analog of the non-abelian Majorana charges in real space. And as I'll argue in a moment, we think that these, again, in phonon systems will be all over the place and could actually be a way forward to capture this interesting physics. And what I'm showing on the right is just a very simple schematic of how this could come about. So for example, you start at the bottom of the diagram with three nodes, one which is plus k minus I plus I, and then the two nodes on the left are braided together as a function of time. And of course, this time could be any external physical parameter that you tune to modify the band structure of the system. And then as you braid this together, then you change, because it's non-commutative, then you change k to minus k and minus I to I. In order to characterize the topology of these compounds, we no longer use things like Chern numbers like we use in single gap topology. Here we use something called the Euler class, and that's what this chi here is representing. So this chi at the bottom, it's a patch capturing the two blue nodes, and it says chi equals 0. That's the Euler class in the system is 0, and that indicates that plus I and minus I can annihilate together. These nodes can annihilate. But then after the braiding with the k node, which is in the adjacent gap, then the minus I becomes an I, and now the same patch Euler class becomes 1, and that indicates that the plus I and plus I cannot annihilate together. So by the simple fact of braiding, we've changed the physics of the system because it's a non-abelian algebra. So this is a very, this is an extremely fast summary of these ideas, and it doesn't really matter what the details are. All that matters is that some of this physics appears in this type of three-band models, and we think that some of it could be really interesting for things like non-abelian braiding. So the key point now is, of course, the following. So now we don't only have a band crossing at a particular gap, we have two band crossings at two different gaps. So if we were trying to study multi-gap topology in electronic systems, and we actually have some work on that as well, but in general, we want to do that because electrons are charged and it's nice to manipulate charges, but it's actually really hard to fully exploit this because essentially we would need two Fermi levels. We would need a Fermi level at the crossing point in one gap, and then a Fermi level at the crossing point in the other gap. So the fact that fermions exhibit Fermi-Dirac statistics with a single Fermi level means that it's really hard to probe, or it places at least strong limitations as to how we can probe multi-gap topology. So that's a big negative to try to study these exotic physics in electronic systems. But you can probably now see where I'm going. In the case of phonons, of course, again, they're bosons, so we don't have a Fermi level. So in a sense, phonons provide the natural platform to study multi-gap topology. we don't mind that we have two gaps at different energies, because we can access both of them when we have bosonic excitations. So our statement here is we think phonons should be the way forward to study this phenomenon. And the reason why we're saying that is because, unlike single gap topology, which has been experimentally confirmed both in electronic and phononic systems, multi-gap topology is yet to be observed in real materials. So it has been observed in some artificial lattices, but is yet to be observed in real materials. And we think that the efforts should be directed in trying to observe it in phononic materials, in phononic band structures. So let me show you very briefly our proposals to do that, and I'll finish after this. So this is an example of one system where we found such multi-gap topology. So this is a silicate monolayer in the Kagome-type lattice. And what I'm showing on the right is the phonon dispersion of this compound. And I'm going to then zoom in into these bands from 20 to 30 terahertz, which form a group of 3 bands and then a group of 6 bands, all of which exhibit multi-gap topology. So I should say that I've been describing multi-gap topology in 3-band systems, but of course you can imagine how you can extend that to multi-band systems. So 3-band system is sort of the minimum you need to have this multi-gap topology, but you can have more complex structures if you go to more and more bands. So in this particular example, we have a 3-band subsystem around 30 terahertz, and then a 6-band subsystem from 20 to 30 terahertz. And then again, what we want to do really to, in this case, induce the braiding is to be able to manipulate manipulate these bands to induce this braiding. And this is what we've been playing around here. So we've been playing both with strain, and on the left and on the right, I'm showing the zoom in the phonon bands under strain for those groups of bands, and then also with an applied gate voltage essentially in the system. So imagine we grow the monolayer on a particular substrate to apply a certain strain, and then we apply a gate voltage. And that gate voltage, again, changes the potential of the system and therefore indirectly changes how the phonons behave in the system. Therefore, you can drive, as I'll show in a moment, this non-abelian braiding in these phonons. So this is the picture. So I really won't go into much detail about the specific process, but all I want to say is that just like it happened in the case of single gap topology, in the case of multi-gap topology, when you move from simple 3-band model like the one I gave in the example to a real material, then the real material has crystalline symmetries, which just make the pictures extremely more complicated because things, for example, get repeated, in this case 6-fold or 3-fold, and so on. But if you have enough patience, you can sit down and you can work through all the topological invariants around these Brillouin zones. And then in this particular case, we can observe braiding as a function of gate voltage. And here I'm showing the braiding in 2 different ways. The top one is again showing the phonon dispersion and showing how the different bands move with respect to each other as a function of gate voltage. And at the bottom, I'm showing those in the full Brillouin zone. Again, how these nodes travel across the Brillouin zone, and you drive the braiding in those. And the key proposal in this material is that the braiding actually, the braiding in this material, because of the crystalline symmetries, actually is all collapsed to the gamma point. And of course, we have a very simple, if you want, approach to study phonons at the gamma point, which is Raman spectroscopy. So we've actually have a concrete proposal for any experimentalists in the audience here as to how to probe the braiding of these phonon modes in this system, which is actually to simply follow the evolution of the Raman peaks in the system. And essentially, the 2 Raman peaks we're interested in are the 2 peaks we're interested in are Raman active, and when the braiding occurs, they essentially come together and then cross. So observing this crossing would be a signature of the underlying braiding that's going on in this material. Of course, one could imagine doing more complex things like neutron diffraction and so on to explore the full phonon dispersion, but we think this could be a simple example to take phonon braiding forward. Of course, the question that may come to your minds now is, what about the bulk boundary correspondence? We've been arguing that the bulk boundary correspondence is also what makes topological materials interesting. In this case, we think the bulk topology in itself, because of this non-abelian braiding, is interesting. But of course, there should also be a bulk boundary correspondence. And what does that look like? And the answer here is that actually the bulk boundary correspondence in multi-gap topology is still unknown. So we still don't understand exactly what the relationship is. So what we did here was simply do some naive calculations and see what we found. And we did find that there were some localized surface states arising from this multi-gap topology, but we still don't fully understand how they come about mathematically and so on. So that's something for future work, which will probably require some people who know more maths than we actually do. And the other thing I want to argue again is that this multi-gap topology may also be in many different compounds in the phonon spectrum. And here I have another example. This is aluminium oxide in this case. And again, we find multi-gap topology in a number of their bands. And again, we can control this multi-gap topology. In this case, with electrostatic doping, for example. We can also do it with gate voltages, but we just put electrostatic doping here as another example. And again, we have braiding here. And unlike the silicate case where the braiding was happening at the gamma point, here it happens around the K point of the Brouillard zone. So again, the ability to access pretty much all the phonons in the system means that we have access to this multi-gap topology in various forms and shapes. Okay, so the open questions here are much bigger than in single gap topology, because as I said, multi-gap topology is yet to be observed in real materials. So it has been observed in some artificial materials, but not in real materials. And we think that one of the reasons is because the efforts to observe it in electronic systems may not be the best approach because of the limitation of Fermi-Dirac statistics. So we propose here, we have a very concrete proposal as to how to observe it in phonon systems, and we think that's the way forward for multi-gap topology. And then, as I also briefly said earlier, surface states are an even more open question in multi-gap topology because the fundamentals of them are still not understood. So that's another big open question. And then, of course, once those are understood, then there's still all the other open questions I discussed about single gap topology, about how we can model these surface states accurately to really try to understand whether we can exploit them, for example, in technologies. Okay, so this is really all I wanted to say about topology, but I have, if you allow me, two more things I will very briefly say. So the first one is that we are recruiting. So I'm about to post 3 postdoc openings. So if anyone in the audience is finishing their PhD or knows any good candidates, then please pass this on. So the ads are not out yet, but they'll be out in the next few weeks. And at least one of the postdocs will be dedicated to studying topological materials. So we've been doing a lot of work on topological phonons, but we also work on topological electrons, in fact. So it's a general position on topology in materials. And the second thing I want to shamelessly advertise is that in Open Science, so I co-host a YouTube channel teaching quantum mechanics. So if you have a chance, so the level is roughly second, third year undergraduates to first year postgraduates. So yeah, if you're interested or know somebody that may be interested, then feel free to direct them to this. It's called Professor M. Science. Yeah, I just want to acknowledge my collaborators. So Bo Peng and Yu Chen, who are the PhD students who have done most of this work. And then on the single gap topology, we've been collaborating with Tiantian Zhang and Suichi Murakami at the Tokyo Institute of Technology. And in multi-gap topology, we've been working with Robert Janslager and Adrian Bohan from Nordita. And thank you all very much for your attention.